Hey guys, welcome back. Mr. Smith here. In the 1930s, as we've seen, physics was a Wild West show with almost an arms race as to who could build a bigger particle accelerator to shoot even higher velocity projectiles at the nucleus. Here's an example. We've already taken a look at the enormous Van de Graaff generators of the early 1930s that were built just in Massachusetts. So you've seen that one in the aircraft hangar in Allston, Mass. before, I think. This is a Westinghouse model. And you get a little sense of the scale of this thing by looking at the man here. The way it worked was the same. You had a Van de Graaff generator would be a friction belt drive that would create static electricity on this dome inside. But what they did was very smart. In this model, they managed to shrink the entire thing to only huge proportions by putting it inside of a containment dome. And so then you could pump out the air, which would lead to sparking and discharges, and pump it full of other gases that would suppress those discharges, and you could get a finer, higher quality beam shooting down this central pipe. And you would do experiments probably in the basement of this building where no one was allowed to go, I imagine, while the machine was operating for sure. But anyway, what was done was all manner of high-speed collisions. And what I want to walk you through is a couple of nuclear transmutations. The game is really easy to play. It's very similar to what we did when we looked at alpha, beta, and gamma emission. So here what I've got is an alpha particle, 2 helium-4, that's a helium nucleus, being smashed into nitrogen, so 7N14, and what we get out is a proton. And what they're asking is just, what's the other thing? So all you do is really easy. You just add up the atomic numbers. So 2 protons, 7 protons makes 9. That means I'm missing 8. So this other character over here has got to have 8 protons. I know that's the atomic number of oxygen. So it's just that easy. So just go ahead and add up the mass numbers. 4 and 14 makes 18, minus 1, and we've got oxygen 17, which is an unusual isotope of oxygen. In this one, we've got 83 bismuth 209 being smacked with an alpha particle, and out we get a neutron and mystery element. So let's go check it out. Same thing. We have a total of 85 protons on this side, none protons on the right. So that means we are dealing with 85, and that turns out to be the element astatine, AT, on your periodic table when you look. Mass number, 209 and 4 looks like 213 minus 1. We've got astatine 212. So cool thing to do. Go ahead and pause the slide deck if you want. Go ahead and fill this one out. Okay, so what you undoubtedly did was to figure out 15 here, 13 there. I must be dealing with an atomic number of 2. That means we're probably shooting alpha particles. Let's just verify. We have element phosphorus 30, 31, and minus 27, and indeed we have a mass of 4. So we're dealing with an alpha particle right here. Okay, so that's transmutation. And so we're going to take a quick look at James Chadwick's discovery of the neutron. What you have always in science is somebody discovering one thing and then another person leveraging that discovery to make yet another discovery. So what we've got here is alpha particles from polonium-210 in Chadwick's device here smacking into a beryllium target. Okay, now alpha particles can't make it through that target, right? Okay, so some mystery particle right here jumps this gap, but this mystery particle is almost undetectable. So Chadwick's detector, when he puts it right here, doesn't see anything. What he does then is put paraffin wax, which is full of hydrogen. It's a hydrocarbon, right? And what he sees is scads of protons being ejected from the paraffin. And he comes to the conclusion that there's a very hard to detect neutral particle that's bridging this gap, the neutron. So neutrons turn out to do 2 things that are really worrisome for you and me. Number 1, they travel through matter really easily, except if the matter contains a lot of hydrogen. That's bad because you and I contain a lot of hydrogen. So if we get hit with neutrons, they tend to be really dangerous because they stop when they hit water molecules. They scatter the hydrogens, and these protons then go off and do further damage because they're charged particles, and they interact strongly with other matter. Anyway, what we want to do is just point out that we've got the neutron now that's going to become an atomic bullet. So if we go forward to 1939, experiments were being done all over the world, but the most important ones were done by Hahn and Meitner in Germany. And what Otto Hahn and Lisa Meitner did was to bombard different atomic elements, heavy ones like uranium, with neutrons. And they found out, well, actually, Lisa Meitner figured out, because this is in the time leading up to World War II, when Lisa Meitner is summarily stripped by the Nazi Party of her rank and her privilege and kicked out of her lab, where she is actually the brains of the outfit. And Otto Hahn is just a skilled chemist. So anyway, Hahn sees a result in the experiment that he doesn't understand and writes to Meitner, who's in exile. And Lisa Meitner writes back and says, "You really ought to check. I think that what you're looking at is barium. And I think what you're looking at is krypton." And Otto Hahn is just blown away. He can't believe that a uranium would fall apart into completely different elements. But he does the test and he pursues it, and he finds out that, yeah, that's exactly what's going on. So what we see in fission is explained by Lisa Meitner like this. You have a neutron. Now, it's got to be a slow neutron. Fast neutrons just zip right through the nucleus, but a slow neutron, one with almost no kinetic energy, has the penetrating power, because it's uncharged, to enter the nucleus and then destabilize it. And there's only a few nuclei that can do this. But what happens is we have in Meitner's idea like a blob of pudding that starts to jostle around like a liquid drop that starts to oscillate with the energy that's been dumped in by the neutron. And then what we get is called fission. We get two completely different chunks of matter out. Now, in this version of fission, we see 3 neutrons coming out. So it was apparent to Lisa Meitner and everybody else who understood this right away that there was a possibility that if you got this to happen, energy would be released, and then these neutrons could catalyze further reactions. So the idea of a chain reaction becomes something of great interest to a lot of people right around 1939. Anyway, what you see here is just the same math that we've done before, and you should be able to do it. But what I find is when I compare all the masses on the left to the masses on the right-hand side is a little bit light. There's a change in mass, and it's equal to 0.186 of atomic mass unit. And I know that if I go ahead and convert that into MeVs over c squared, that's 173 MeVs per c squared of mass, and then by E equals mc squared, this is a hellaciously powerful reaction. So 173 MeVs per c squared times c squared, and you get 173 MeVs from a single fission. That's enormous. It's just huge, huge, huge. So let's go and see what people did with it to make it practical. So what you see here is the first nuclear reactor built by Italian physicist, also in exile in the United States at this time, Enrico Fermi. What he did was to commandeer a squash court next to the University of Chicago's football stadium and build this reactor there. In about 3 months, they got the result that they were after. They used graphite as a moderator, and they successfully achieved the first sustained nuclear reaction of fission ever in the history of the world. And here's a look at how it could happen in a modern reactor. This, however, is one big difference. We would not do this in the United States. This reactor that they're showing you here has graphite still being used as a moderator. That's not our choice in the US because graphite can catch fire. It's what happened in Chernobyl, and it caused a whole secondary series of issues. But what you see here is a kind of a normal design for a reactor in other ways. You have fuel rods that can be raised and lowered for exchanging them, and you also have this moderator assembly that can be raised and lowered. And the idea is that by combining that, you can get a critical mass of enough nuclear material in the same place that fission can take place, and also enough moderator to slow down those neutrons so that it sustains itself. So you're probably aware that 2 of these atomic weapons were used in wartime over Hiroshima and Nagasaki. What we're looking at is an image here of the 4th atomic bomb blast done after the war, where the scientists were trying to understand the real yield of these things and understand them in a more scientific way. However, it's really important to me as a human being to point out that the knowledge that was gained during the Manhattan Project and following it wasn't just devoted by people looking to build bigger weapons for war that was already the most brutal in human history. What they were looking for in many cases was the deeper understanding about how the universe works, and that you can see reflected in our understanding of how the sun operates. So it's a never ending source of fascination for me to consider what the sun really is. So we'll just light up this quick image here. The sun is an ongoing nuclear fusion explosion, and the power of it dwarfs the power even of the atomic explosions. And so we'll do this analysis of the equation that you see here in class. You can see in some way a reason for the enormous energy release in the sun because of our understanding of binding energy to pernucleons. So when we climb towards more stable isotopes, we get a release of energy. And so you can see iron being the most stable. We'll talk about the relationship between uranium and hydrogen and why they work. But to go out quickly, I wanted to point a couple of things out that you might find interesting. So you can pause the deck here. These won't be on any test, but if you want to talk about them in class, I'm up to talk with you. This is our current understanding. It's a thing called the Standard Model. And what it does is links together fundamental particles and forces with all of the known behaviors in the physical universe. So some of these particles are things you would have heard of. Some of them are things that you may not have heard of. But what they do is they all fit together to explain, with the knowledge that began in the Manhattan Project, things like this nebula. So this is a thing that exists in our own galaxy. The Helix nebula is the remnants of a supernova explosion, and you're seeing elements backlit by ultraviolet light streaming out of the supernova center. You have star formation that's going on, and this is a beautiful image on the left of something in the Orion, also in our own galaxy, where these pillars or spikes that look almost like a lightsaber are energy being ejected and matter being ejected from the poles of this forming sun as matter crashes down onto it. You have this event, which is not a supernova, but was a very significant event in an unstable star in this star Eta Carinae, which is not in our galaxy. It's 7,500 light years from us. But this was an event that was recorded in 1840 on Earth as a big flash. So it's just a crazy example of the dynamic nature of the cosmos. And finally, we have the literal gravitational interaction of companion galaxies, where the small galaxy on the right is passing slowly by the larger galaxy on the left, and it's actually shepherded, as in the rings of Saturn sort of shepherded the structure of the larger galaxy and really honed the spirals that you see. So anyway, our knowledge of the universe is so much bigger than you may be aware of, even extending back into the earliest moments of existence. So there's a lot to talk about there, but all this knowledge really goes back to the early moments when we began to understand what really made the nucleus work. So bring questions to class if you have some. Good to talk with you, and we'll see you soon. Bye-bye.